Hey guys, my name is IBM and I'm still taking you through the past paper questions of magnetic fields and electromagnetic induction. I think this document has about 114 questions from different past papers right from 2001 up to 2025. So I think this is going to be part 16. This is part 16 starting from question 45. A small coil of wire is situated in a uniform non-magnetic field as shown here. So the magnetic field is not uniform. The coil has 40 turns of wire and moves at a constant speed. It moves at a constant speed in a straight line. The coil has displacement x from a fixed point P. So it has displacement x from P. The variation with x of the magnetic flux phi in the coil is shown in the figure here. So the magnetic flux decreases and then it increases. This is at 3, this is 3 times 10 to the power minus 6 Weber. Okay. The coil is moved at a constant speed between point P and the point where x is 3.0 centimeters. Calculate the change in magnetic flux linkage. So we know that flux linkage or change in flux linkage is going to be equal to n number of turns times change in magnetic flux phi. So if we had area and number of if we had area and magnetic flux density, we would use NBA, because remember magnetic flux is equal to B times A, where B is perpendicular to the area. So the change in flux is going to be number of turns times change in flux linkage is number of turns times change in flux, and flux changes from 5 to 3 times 10 to the power minus 6, and the number of turns is 40. So this is going to be equal to 40 times the change in flux, which is 5 minus 3. Then I multiply this by 10 to the power minus 6. So this is going to be 40 times 2 exponent minus 6. So this is giving us 8.0 times 10 to the power of 5. This is 8.0 times 10 to the power of 5, minus 5 actually, minus 5 Weber. The EMF induced in the coil is 5.0 times 10 to the power minus 5 volts. Determine the speed of the coil. So remember, EMF, or the induced EMF, is equal to the rate of change of flux linkage. Induced EMF equals the rate of change of flux linkage. So the induced EMF E is going to be number of turns times the change in magnetic flux, of course, divided by time. And they want us to find the speed. So this means that the time, if I wanted to find the time here, this statement implies that the time of change of flux is going to be equal to the flux linkage, or change in flux linkage, which is N change in flux divided by E, which is going to be 8.0 times 10 to the power of minus 5. That is the change in magnetic flux linkage, divided by E, which is 5.0 times 10 to the power of minus 4. So when you divide this, you have the answer divided by 5 exponent minus 4. So this is 0.16 seconds. So that is the time. Because the speed is constant, because they said the coil is moved at a constant speed, so we want to find that constant speed. We know that speed v equals to the distance divided by time. Now that we know the time, we just look for the distance. X was 3 centimeters, so this is going to be 3 times 10 to the power of minus 2 divided by time, which time is 0.16. So you have 3 exponent minus 2 divided by the answer. So that is 0.1875. 0.1875, or I'll write 0.19 meters per second. Alternatively, I would just relate these two equations and then come up with just a single equation. For example, induced EMF is equal to number of turns times magnetic flux, change in magnetic flux linkage divided by time. And also we know that V equals to the distance, which is now going to be X over T over delta T. And this means where there is delta T, where there is time, I'll put there change in X over V. Then I'll substitute for that in that equation. So this means that EMF is going to be equal to N change in magnetic flux. Where there is T, I'll put change or X over V, which is the same as N change in flux, N change in flux, then times V, then divide by change in X. And here you can now make a simple substitution where you make V the subject. V is going to be equal to N change in flux divided by E times X. When you make a substitution, that will be 8.0 times 10 to the power of minus 5 divided by E, which is 5 times 10 to the power of minus 4, then times X, which is 3 times 10 to the power of minus 2. I'm sure the answer is exactly the same, 0.1875 meters per second. Okay, so this is just doing algebra at once and making substitution at once. On the figure 10.3, sketch the variation with X of the EMF E induced in the coil for values of X from X equals to 0 to X equals to 6 centimeters. So remember that the EMF is induced EMF is directly proportional to the rate of change of magnetic flux linkage, which rate of change of magnetic flux linkage is directly proportional to the gradient of this graph. So the induced EMF is directly proportional to the gradient of this graph. Notice that they are straight lines, so the gradients are constant, but this is a negative gradient and this is a positive gradient. That means the EMFs correspond to the different time intervals will have opposite signs. They will have opposite signs. Because EMF is directly proportional to gradient, a constant gradient means a constant EMF. So we have a constant EMF here, which we have actually seen, which has actually been given as 5.0 times 10 to the power of minus 4. Then we just check the relationship between the gradients. The gradient this side is actually 5 minus 2 divided by 3. I'm ignoring the power of 10. So this is like 2 over 3. I'm just trying to compare the gradients. The gradient this side is going to be 7. Is it 7? No. Yeah, it is 7. 7 minus 3 divided by 6 minus 3. The gradient this side is 4 divided by 3. So you notice that the gradient this side is 2 times. So this side gradient is 2 times because 4 over 3 is the same as 2 times 2 over 3. So the gradient on the left hand side is 2 times, the gradient on the right hand side is 2 times the gradient on the left hand side. Therefore, the EMF on the left side is going to be twice on the right hand side, the EMF is twice the EMF on the left hand side. So between 0 and time equals to 3 seconds, the EMF is half the EMF on the other side, represented by the gradient on the right hand side. And remember, these are supposed to have opposite signs. So I'll just try to use the same number of squares here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 15. So I'm just only going to use, let's say, to maximize this. Because there are 15, I'll use 7. 1, 2, 3, 4, 5, 6, 7. Okay. So because the gradient was constant, it means the EMF is constant. 1, 2, 3, 4, 5, 6, 7. Okay, that is a constant EMF, so it will be a horizontal line. Then the other one, because the gradient after 3 seconds, after 3 centimeters is twice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so your graph will take this shape. You can draw a better one, but it will take this shape. Okay, so the gradient will take that shape. Define the Tesla. Now this is a long definition. You see it is 3 marks. You and me know that the Tesla is a unit of magnetic flux density B, and we know that the magnetic force on a conductor is given by B sine of theta, and which means that B is going to be equal to F divided by I L sine of theta. If if B is perpendicular to the current I, it means that sine theta is going to be equal to 1. If B is perpendicular to the current I, so sine theta is equal to 1. So that means 1 Tesla will be equal to 1 Newton divided by I, which is 1 ampere, times L, which should be 1 meter, if B is perpendicular to I. So from that analogy, we can now define the Tesla. So the Tesla is a unit of magnetic flux density, a unit of magnetic flux density of a uniform magnetic field. Of a uniform magnetic field, normal or perpendicular, to a long straight wire carrying a current of 1 ampere and causing a force let me say, causing a force per unit length of 1 Newton per meter. So unit of magnetic flux density of a uniform magnetic field normal to a long straight wire carrying a current of 1 ampere and causing a force per unit length. That is force over L of 1 Newton per meter. So that is the ampere. It's actually force per unit current per unit length acting on a long straight conductor placed perpendicular to a uniform magnetic field, that is a Tesla. A charged particle of mass m and charge positive q is traveling with a velocity v in a vacuum. It enters a region of uniform magnetic field of flux density B as shown in the figure here. The magnetic field is normal to the direction of motion of the particle. The path of the particle in the field is the arc of a circle of radius r. Explain why the path of the particle in the field is the arc of a circle. So we have answered a similar question many times. One, we have been saying the magnetic force on the particle is constant and is always perpendicular or normal to the direction of motion, and the direction of motion and the speed of the particle. It is always perpendicular to the direction of motion and perpendicular to the speed of the particle or to the velocity of the particle. So the magnetic force does not change the speed, it does not change the kinetic energy, so there is no work done. It just provides a centripetal force or centripetal acceleration. So I would say the magnetic force on the particle is constant and always perpendicular or always normal to the direction of motion. And the speed of the particle. It's always perpendicular to the direction of motion and the speed of the particle or the velocity of the particle. So the magnetic force does not change the speed because they are always perpendicular. So the magnetic force does not change the speed, does not change the kinetic energy, so there is no work done. Does not change the speed, but just provides the centripetal force. Just provides the centripetal force, or call it the centripetal acceleration. It just provides the centripetal force or the centripetal acceleration. Okay, so it means the particle is going to move in an arc of a circle, because for centripetal acceleration, the acceleration is always perpendicular to the velocity, so the force acts towards the center of the circular path. Show that the radius r is given by r equals to mv over bq. So since the magnetic force provides the centripetal force, we shall just equate magnetic force to the centripetal force. Therefore, we equate BQV equated to mv squared over r, which means that BQ is equal to mv over r, which implies that r equals to mv divided by bq as required. A uniform magnetic field is produced in the region PQRS as shown in the figure here. So this is the figure. The magnetic field is normal to the page at point X. So the magnetic field is perpendicular to the page at point X. A gamma ray photon interaction causes the particle to be formed. Sorry, a gamma ray photon interaction causes two particles to be formed, as we can see with those two different paths. The paths of these particles are shown in the figure. Suggest with a reason why each of the path is a spiral rather than the arc of a circle. So we have a uniform magnetic field here, and they are saying the magnetic field is normal to the page. The magnetic field is perpendicular to the page. At point X, a gamma ray photon interaction causes two particles to be formed. The paths of these particles are shown in the figure. Suggest with a reason why each of the paths is a spiral rather than the arc of a circle. So the paths being a spiral rather than the arc of a circle suggests that the speed of the particles is changing, or the momentum of the particles is actually changing. And of course, we know that from the previous equation, we have that radius equals to mv divided by bq. We have seen that above, which means, and we see that we know that mv is momentum. So it means that momentum, which is mv, equals to bqr. If the path is spiral, it means the radius of the path is decreasing, and the decrease in radius is suggesting that there is a decrease in speed or a decrease in momentum of the particles. So the reason as why the path could be spiral is one, the momentum or the speed of the particle is becoming smaller. So the momentum or the speed of the particles is becoming smaller. This implies that the radius must also become smaller, resulting into spiral paths as shown here. So the radius must also become smaller, resulting into the spiral paths. Okay, so it means that now here the speed of the particles is changing, because we are seeing they are becoming spiral, which means the speed of the particles is changing. And because the speed of the particles is changing, it is because the particles might be the speed of it's because the momentum of the particles is actually changing, and the decrease in the radius of the paths implies that the particles are actually now moving slower because the radius is becoming smaller. State and explain what can be deduced from the paths about the charge on the two spheres. We see that it's like the particles are moving away from each other, and that means that the charges could be having the same sign. So the spirals are in opposite directions, so the particles have opposite charge. This is a magnetic field. The particles are moving away from each other, and in a magnetic field, a positive and negatively charged particle move in opposite directions. So these should be having opposite signs. If they had the same sign in a magnetic field, they would be moving towards the same side. Okay, so the particles or the spirals are in opposite directions, so the particles have opposite charges. The spirals are in opposite directions, so the particles have opposite charges. If they had the same sign, they had the same charge, in an electrical or magnetic fields, particles with the same charge are deflected towards the same side or in the same direction. So because they are deflected in opposite directions, because they have opposite signs of charge, then the initial speed of the two particles. Now notice that all the particles start from the same point, and the radius of the path is almost the same from the start, which means that they must have started from the same, or they must have started with the same initial speed, because we see that speed is directly proportional to the radius. So the initial radii of the paths are equal. The initial radii is plural. The initial radii of paths are equal, and so the initial speeds are equal. We have just said radius is directly proportional to speed from the equation above. Positively charged particles are traveling in a vacuum through three narrow slits S1, S2, and S3, as shown here. Each particle has speed v and charge q. There is a uniform magnetic field of flux density B and a uniform electric field of field strength E, so it's a crossed field, in the region between S2 and S3. So there's a uniform electric field here, in this region here. State the expression for the force acting on a charged particle due to the magnetic field. Of course, for a charged particle due to a magnetic field, know that the force is equal to BQV sine of theta, or it can be BQV cos of theta, depending on whether the angle is between the magnetic field and the direction of the particle, or between the normal to the direction of the particle and the magnetic field. So it can be cos or it can be sine. Then the electric field, of course, the force to electric field depends on the charge and the electric field strength. So the force is equal to Q times E. The electric field acts downwards in the plane of the paper as shown in the figure. State and explain the direction of the magnetic field so that the positively charged particle, the particle is positive. The direction of the electric field on a positively charged particle is the same as that of the electric field. So since the electric field is downwards and the particle is positive, it means the electric force is going to be downwards, which implies that the magnetic force must be upwards. So the force due to the magnetic field is going to be upwards. Okay? State and explain the direction of the magnetic field so that the positively charged particles may pass undeviated through the region. So I've already explained that because it is positively charged, the direction of the electric force on a positively charged particle is the same as that of the electric field itself. So the electric force is downwards. For the particle to pass undeviated, the magnetic force is going to be in the opposite direction, equal but opposite. So the magnetic force is going to be upwards. Now we bring in Fleming's left-hand rule to predict the direction of the magnetic field. So with the thumb pointing the direction of the magnetic force upwards, because the particles are positively charged, the second finger points in the direction of the particle. And when you try to use Fleming's left-hand rule on the paper, if you are holding it in the vertical plane, the first finger points towards the paper. Or you can try to stand and place the paper on the table. Try to place the second finger in the direction of the particles and the thumb to the top of the page. Still, the first finger points into the page. So, the question state and explain the direction of the magnetic field. So, I will start this by the explanation, and I will say that the electric force on the positively charged particle is in the same direction as the electric field. So the electric force is downwards. Electric force on a positively charged particle is in the same direction as the electric field. So the electric force is downwards or towards the bottom of the page. Then number 2, for no deviation, if there should be no deviation, so for no deviation, the magnetic force must be in the opposite direction. Must be in the opposite direction to the electric force. So magnetic force is upwards or up towards the top of the page. Thus, by Fleming's left-hand rule, by Fleming's left-hand rule, the magnetic field must be into the plane of the paper. By Fleming's left-hand rule, the magnetic field must be into the plane of the paper. So the magnetic field must be into the plane of the paper as illustrated with this diagram here. Just understand the logic. The electric field is downwards, but the particle is positive. The force on a positively charged particle is always in the same direction as the electric field. For no deviation, the magnetic force must be equal but opposite to the electric force. So the magnetic force must be upwards. By Fleming's left-hand rule, if the magnetic force is upwards, the thumb points upwards. Because the particle is positive, the second finger points in the same direction as the particle's motion. And by doing that with your left hand, the first finger points onto the page as illustrated here. So the magnetic field is into the page. Okay, see you in part 16. Until next time, bye bye.